Welcome to session number 9. As you know, we concluded our discussion of IPOS programming. We're now shifting gears and we're moving forward into what I consider really the exciting part of this class, and that is motion control. In other words, what we're actually trying to do, the whole reason for IPOS. We built the bedrock by learning most of the key details of the IPOS programming language, and now we're moving on to using it to do actual things, in other words, applications. Where do we begin? Well, we need to cover a few big ideas here that will lead us into our topic for today. Our big ideas deal with a subject called referencing. Most IPOS programs involve positioning. Not all of them, certainly. There are some speed and torque control ones, but a good percentage of IPOS programs do involve some kind of positioning. And as you probably know, positioning requires that you have an encoder on the motor and sometimes other encoders as well. Why do we need encoders? Well, it's really simple. We need to know where things are, and without encoders, we can't do that. If you've done anything with encoders and positioning, you know that encoders require referencing. Referencing is really a very big idea, and that's the reason we're really here, because it's a complex topic. I want you to understand referencing, because if you're going to work with referencing, you really need to know how it works and how it's handled in the Movie Drive B. So it's really essential that you understand referencing so you can use it intelligently. Let's dive in and spend some time learning about referencing. Referencing is also called zeroing, and I like to think of it like zeroing a kitchen scale or a laboratory scale. You turn the scale on and it probably doesn't show zero exactly because the pan has a certain amount of weight. What you do is you punch that zero button, and that sort of eliminates the weight of the pan and tells the scale, don't think about that, get ready for what you're going to throw on it in order to weigh it. Well, that's a similar idea with referencing an encoder. What you're doing is establishing what's called the machine zero position, which in SEW literature is usually abbreviated MZP. So you're establishing zero, where in the travel range we consider the 0 point. And everything is relative to that, usually positive or negative, sometimes just one or the other, but often both. And you've got to establish that. We do that when we reference the encoder. All positioning systems, no matter what style of encoder you use, must be referenced at least once before they can be used to position. Now, if you have an incremental encoder, these have to be referenced every single time you start up the VFD, because incremental encoders lose their position when you switch off the power, and you have to zero them every time you power up. On the other hand, there's a second category of encoder called the absolute encoder. It does not have to be re-referenced every time you power it up. When you turn it on, it knows where it is. It remembers where it is. The only time you have to reference an absolute encoder is after you've installed a brand new one, or if you make changes to the application. If something moves or gets altered, then you have to do another referencing operation. So that's why I say everything has to be referenced at least once. If you don't understand the difference between an incremental encoder and an absolute encoder, don't worry about it. We're going to cover that in just a second. Of course, if you do, then you can just sort of snooze through that section or listen to it for a quick review. Now, the way the system finds where the MZP is, the machine zero, it's called the referencing mode. There are many different ways to find the zero position. And as it happens, the Movie Drive B actually supports 9 different referencing modes. We're going to cover all 9 of them so you understand how they work. Now, it's not quite that formidable. There's really only 5 categories of modes, and there are sometimes 2 modes in a category, and the only difference is which direction the drive searches for the MZP, goes to the left or to the right, clockwise or counterclockwise. It's really not that bad to understand this, but we're going to go through it anyway. Before we do that, I want to review encoders, so I'm sure you understand how they work. The incremental encoder is very popular. It's a common motor encoder that goes on the back of the motor. They're relatively inexpensive as encoders go. The way they work is they use what's called an interrupter disk to detect motion. And you can see one that I've opened up and photographed. Let me show you, though, what an interrupter disk would look like in a little more detail. This particular interrupter disk is a glass disk, and it's attached to a shaft which is coupled to the motor. And you can see it's got light and dark areas on it. These are called tracks. There's a sensor on one side of the disk and a light source on the other, and as the disk turns, the dark areas break the light beam and the sensor detects that. Now you're looking at this and you're probably thinking it looks like there are several different areas on the disk that interrupt the beam, and that is true. So here's what they are. There's the A track, that's the first track with lots of little marks on it. And there's the B track, which actually is identical except it's shifted slightly. The reason we do this is by having two tracks that are offset from each other, you can figure out which way the disk is turning as well as how fast it's turning. There's also often a third track called the zero pulse track or the index track. There's just one mark on there, so it can detect just a single revolution of the disk. It's often used during referencing because it allows you to get the encoder in a known orientation. I will mention that not all incremental encoders have a zero pulse track. Many do, but some don't. Therefore, you need to know if it's present or not if you wish to use it as part of referencing. Now, absolute encoders, what's the difference? Well, incremental encoders simply generate pulses, and by counting the pulses, you can estimate where you are. It's kind of like the odometer on your car. As you drive, it goes through tenths of a mile, and that lets you know how far you've traveled. An incremental encoder works identically. An absolute encoder, and here's one that I've taken apart, is a little different. It actually outputs a number which indicates where in its rotation it happens to be. And many absolute encoders can count revolutions as well and keep track of multiple turns in addition to simply its 0 to 360-degree rotation. You can see the advantage of an absolute encoder. It gives you an actual position, whereas an incremental encoder, you sort of have to deduce the position by how many pulses you've counted. Absolute encoders, though, often include incremental tracks, which can be used for monitoring the motor's speed. They're really often combinations of absolute and incremental. Here's an encoder disk from an absolute encoder. It has actually 3 different regions on it. It's got the incremental track on the outside. That's just a series of interrupter marks. It's got a zero pulse mark on it as well. And then the interesting thing is in the center, this section is a series of tracks that encode a binary number for each position. And the sensors read these and output a number, basically a modified binary number that indicates where in the 0 to 360-degree rotation it is. And as I said, many have a rotation counter as well, where they keep track of multiple rotations. Absolute encoders are usually a lot more expensive because they're a lot more sophisticated. Now listen up, this is really important. If you connect an encoder to the motor on a MoviDrive B and plug it into the X15 connector on your encoder card, the MoviDrive B will call that the motor encoder, and it will scale it so that it always generates 4096 increments per revolution. Now this is true regardless of the actual resolution of the encoder. Encoders are sold based on their resolution, how many increments per revolution. Cheap encoders have fewer, expensive ones have more, but the MoviDrive always scales it. So that is the number you're always working with on a MoviDrive B. There are other connectors that you can connect other kinds of encoders to, and they are not bound by this rule, but this is true of the motor encoder, which is connected to X15. All right, well, let's talk about referencing now that we've gotten encoders out of the way. Besides the encoder, there are usually sensors which are used to help you reference the drive. One possible sensor is a pair of limit switches. You probably know what these are. They prevent movement outside of normal travel limits. They trip a fault on the inverter if you touch a limit switch, so they're a kind of safety device. For example, this is a horizontal track with a carriage that travels left and right. There's a limit switch at each end, and if the limit switch gets bumped by the carriage, it means it's ready to go off the end, and that shuts down the VFD. Limit switches are normally closed. They're what are called active low sensors. That means they output a voltage when they're not being touched, usually 24 volts. And when you touch them, they output a low voltage, something close to zero. They do this as a kind of fail-safe mechanism. If a wire gets cut or a power supply fails, it trips the limit switch by going low. Let me show you the limit switch in action. As you head toward the left limit switch, you're high, but when you touch it, it goes low. And then when you move off it, it goes high again. The right limit switch works the same way. It's normally high, but when you touch it, it goes low. And when you move off it, it goes high again. Limit switches, besides being safety devices, can be used during referencing. They can be used to detect the position, because of course, if you bump the limit switch, you are in a known position. We will see several referencing modes do use the limit switches. Another common referencing sensor is the zero pulse, if your encoder is equipped with one. We call this zero pulse detection. It determines the known mechanical position of the encoder. Basically, what you do is you just rotate until the zero pulse goes by and then you stop. It may take up to a full rotation to reach the zero pulse mark if it's just gone by, or you might trip it immediately if you're sitting right next to it. The zero pulse can be used by itself. There's one referencing mode that just uses it, but it's often paired with another sensor where you trip a sensor and then you keep rotating until the zero pulse happens. Let me show you an example of just zero pulse by itself. You move, and as soon as that pulse comes, you say, all right, I got the zero pulse, stop, I'm done. I'll show you how this works for referencing in just a minute. The third referencing sensor possibility is called a reference cam. It's a contact sensor that detects the position when you touch it. It can be anywhere in the travel range. Here it's in the middle, but sometimes it's near the limit switches. There are really no rules for using a cam. It can be anywhere. Reference cams are normally open. They are active high sensors. When you're not touching them, they output a low voltage close to ground. And when you touch them, they output a higher voltage, usually 24. They do this because they're not devices that have to be fail-safe. They're only used for referencing, which is not really a safety situation. You can use a cam by itself. You can use it in combination with limit switches, or you can sometimes even use it with a zero pulse. Let me show you an example of the reference cam used just by itself. All right, we're going to start moving till we touch it. Notice it's low. We move till we touch it. It goes high when we're on it. And then what we do is we back away just until it goes low and then stop. That's a very popular way to reference. We can also use it with the zero pulse if our encoder is equipped with it. Here's an example of using the cam plus the zero pulse. We move to it, we touch it, goes high, we back off till it goes low, then we keep moving until we get the next zero pulse, and then we stop. That causes us to move a little further in most cases. That just puts the encoder in that known position. That's an option that may be available as well. All right, we've come to the referencing modes. We're going to go through all of them, and this won't actually take as long as you may think. Many of them are duplicates that just have subtle differences. Let's look at them here. There are actually 9 modes that you can select, and you may remember that we picked reference mode 1 when we configured our drive for IPOS programming. So there are 9 choices, 0 through 8, that you can set in the parameter tree. But they divide really into 5 categories, 5 different categories. There are actually 13 total because some can be used with or without a zero pulse. Here we go. Let's summarize them. There's zero pulse detection alone. That is one mode. There's also a reference cam type number 1, which can be used with or without a zero pulse, and it can go either to the left or to the right. That means there's actually 4 possibilities here. There's left and right without a zero pulse. There's left and right with a zero pulse. You can move either to the left or right limit switch, and this always works with the zero pulse, so there are 2 possibilities here, left or right. There are 2 no travel referencing where the drive doesn't actually move. The only difference is one is with and one is without the drive enabled, so there are 2 there. And there's another reference cam version with or without zero pulse, either to the left or right. That means there's 4 there. If we add all these up, we get 13 total, but you can see there's really only 5 categories we have to actually understand. So we're going to go through the 5 categories. All these modes are available with application modules if you do that instead of writing IPOS programs. But of course, we care about IPOS, that's why we're here, and all of them are available under IPOS as well. You should know that referencing takes place at 2 different speeds. Speed 1, which is a faster speed, speed 2 is slower. You set these in the parameter tree. Generally, the idea is you use speed number 1 to get to the sensor, so you go quickly, and speed number 2 to move away from it, which is a much slower speed for more precision motion. All right, let's look at the different modes. We're going to start with mode 0. This is a really easy referencing mode. Basically, the drive moves in the left direction until the very first zero pulse comes from the encoder. Obviously, you must have an encoder with an index track, a zero pulse, otherwise this won't work. So here's what happens. You run counterclockwise, which is to the left, at the slower speed, speed number 2, until you get a zero pulse. Here we go. So you sort of creep till the pulse comes, and then you say, bingo, I'm referenced. Pretty simple. All right, that's our first mode. Mode number 1, the goal is to wind up to the left of a reference cam. So you have a reference cam usually somewhere near the middle of the travel range. Your goal is to wind up on the left side. What you do is you run counterclockwise, that's to the left at the higher speed until you touch the cam. Sort of like this. All right, you've touched the cam. Then you keep moving at the slower speed until you come off the cam. And you can optionally, if you wish, wait until the next zero pulse, but you don't have to. You can just stop as soon as you get off the cam. So here we go. We move slowly until we just clear the cam, and then we say we're referenced, or we go to the next zero pulse and then say we're referenced. Pretty simple. Mode 2 is exactly the same as Mode 1, except you move to the right, and your goal is to be on the right side of the reference cam. Other than the position you wind up in the end and the direction you travel, it works just the same way. So that's Mode 2 out of the way. So Modes 1 and 2 are kind of a pair of modes. Mode 3, you travel to the right limit switch. You move right clockwise at the higher speed until you touch the limit switch, like this. Boom. Then you move off it to the left at the slower speed just until it releases, and you keep moving until the next zero pulse. So this one always uses the zero pulse, sort of like that. Moves off it, waits for the zero pulse, and then says, I'm referenced. As you can probably guess, Mode 4 is the same thing. It uses the other limit switch. It's otherwise identical. So Modes 3 and 4 are also paired together, with only the difference being the travel direction and the limit switch. Mode 5 is what's called No Travel Type 1. With this mode, all you do is you trigger it, and whatever the current encoder value happens to be, you say, I'm at 0, that's the reference point. There's no powered motion at all. So you simply say where I am now, that's it. However, the drive has to be enabled for this to work. You can't have a disabled drive. So here's what happens. Boom, I'm referenced. We often use Mode 5 in class because it's a quick, easy way to reference when you really don't care, when you're just working with a demo unit. It's also often used with absolute encoders. You get the drive manually positioned where you want it to be, and then you say, here's 0, bingo, and that's your one time you reference the drive. So mode 5 is often used for that, but it can be used with incremental encoders. Now there's mode 6. In this one, you travel to a cam that is sitting right in front of the right limit switch. So you move to the right until the cam is contacted. You do this at the higher speed, like this. And then you back off until you release it. And you can optionally keep moving until the next 0 pulse if you wish. So here we go. You just back away till it releases. Maybe you go to the 0 pulse, maybe not. And then you stop and say, I'm referenced. Mode 7 is the same thing. It's just on the other end. It's identical to mode 6. Again, travel direction's the opposite, and the cam is in the other position, but it's the same. So mode 6 and 7 form a pair. And now here's our last referencing mode. It's mode 8. It's the second no travel type, so it's actually paired with mode 5, and it works almost the same way. But the difference is it does use the current encoder value as the reference point. Again, no powered motion occurs, but the drive does not have to be enabled. This is often handy because if the drive isn't enabled, you can just manually usually slide the mechanism around to the position you want and then trigger it. So what people often do is they manually move it around. And as soon as they get it at 0, they trigger referencing and they say, okay, there you go, you're referenced now. So modes 5 and 8 are very similar. So they form a pair. And that is it. That's all our referencing modes. Another thing to understand, and this can be kind of tricky for a lot of people, is reference offsets. Reference offsets are used in certain applications and not others. Now let me explain what a reference offset is. The distance between the referencing sensor and wherever you've decided machine 0 is called the reference offset. You may be thinking, well, isn't the sensor always at 0? The answer is no. Sometimes it's at the actual 0 position, like here, for example, where we have a cam in the middle of the travel range, and it happens to be sitting at machine 0. In this particular situation, we say the reference offset is 0. In other words, there's no difference between the sensor and 0. They're both in the same place. So we just set the offset to 0 and then we forget about it. But there are situations where the sensor is not the actual 0 position because of the application requirements. Notice here 0 is in the middle of the travel range. It's in the middle of the track. The sensor, on the other hand, which is a reference cam, is off by the right limit switch. In this case, 0 and the sensor are in two different places. What we do then is we measure the distance between the sensor and the actual machine 0. And we do have to think about a sign, plus or minus. We have to know if it's in front of or behind the sensor. In this case, for example, machine 0 is in the middle and the sensor is 28,504 increments in front of it. Therefore, we use a positive sign. The sign indicates the relationship of the sensor to 0. Now, if we were on the left limit switch, we'd have a negative offset because it's behind 0. So what we do is we just put in the number 28,504. That's a positive number, and that tells us where the sensor is in relation to 0. Just remember the sign is positive because the sensor is clockwise of the machine 0 position. If it's counterclockwise, it's negative. Easy way to remember it. All right, now let's go back to a situation where machine 0 is the same location as the sensor. In other words, reference offset is 0. If we set the reference offset to 0 and we have just referenced the drive and then we ask it what its position is, it will say, I'm at 0. No big surprise. So it'll say 0. And if I say, go to position 0, the drive won't move. It'll just say, I'm already at 0, so there's no reason to move. But on the other hand, if we have this kind of situation where 0 is here and the cam is behind it, we would have a negative reference offset. If the reference offset is not 0 and we have just referenced the drive, it's actually going to report its position as equal to the reference offset because it isn't at 0. Even though we've just referenced it, it's sitting behind it, minus 25,020 increments behind it, in fact. And if I tell it go to 0, it's going to do this. It's going to move to 0, and then it'll say, okay, now I'm at 0, because now I'm at the true machine 0 position, not at the sensor. That's a subtle difference, and once you understand it and internalize it, it makes a great deal of sense. So be sure you understand this. Offsets are important, but they are a little confusing at first. Now let's look at the parameter tree in the Movi Drive B, because there are a number of parameters that are important for positioning. We're going to start with the reference offset. It's in parameter P900, so that's where you program your reference. Don't forget the sign. If it's negative, be sure to put a minus sign in. Here are our two referencing speeds, speed 1 and 2. So we usually set these to somewhat slower speeds for more accurate referencing. P903 has the referencing mode. This is a number 0 through 8. This is where you pick the mode. You've been here before. So these are the parameters we typically care about. Now, what we often will do is, if we're using sensors, we'll associate them with some of the built-in digital inputs. For example, if you have a reference cam, you may associate it with one. This is what we selected when we set up our drive. We assigned it to DI03. You can also set up limit switches. We did this as well. You can assign these to DI04 and 5, for example. It's fairly common to associate a few signals with the binary outputs, so you can use them for status information. When we set our drive up, we set DO03, which is a built-in digital output, to the IPOS reference signal. That indicates when the drive is actually referenced successfully. DO04 indicates when it's in position. That is handy because when you do a travel operation, you want to know when you've arrived. And there are some system variables too that you sometimes will want to query to find out what's going on. Status word, which is a very important system variable. It's in H473. We will be using it a lot now that we're getting into actual motion control. Has a nifty little bit number 20, that goes to a 1 when the drive is referenced and 0 when it isn't. You will definitely be looking at that bit a lot. There's another system variable called active position motor. It's in H511. That has the actual position based on the motor encoder, the one connected to the X15 connector, and it does incorporate the reference offset into the number it gives you if you're using a reference offset. All right, crucial point. Listen very closely. Some system variables do not accurately reflect the drive's status during the first few seconds of operation after you run your program. What it's smart to do is do a wait 5000 at the beginning of your program. That's a 5-second wait. You put this in the initialization section, and once this time has elapsed, the system will have stabilized and the system variables will be accurately reporting what you care about. So really smart idea. If you read them immediately, you might get some wrong numbers. Now, there is one function built into the library of built-in functions associated with referencing, and it is called GoZero. You've actually seen this before. I used it as an example way back. It has one parameter called type, and GoZero performs some kind of reference travel. Type does not repeat, does not set the mode, in other words, 0 through 8. You have to do that in the parameter tree. What it does, it configures the existing mode. Now, we have picked mode number 1 when we set up our system for IPOS programming. You may not remember that. We did that many sessions ago. We picked mode 1, which uses a reference cam, and the type parameter doesn't change that, but it allows you to tweak it. How does it do it? Well, you feed it one of these constants. These are defined in constant b.h, that header file that you're always including. These are actually associated with numbers. You don't need to worry about the numbers. If you want to go and look at constant b.h, you can see the numbers. But you feed it these constant values. They're all uppercase, and they tweak how that mode, in our case mode number 1, behaves. All right, so what does all this mean? Well, it's really just lots of combinations of different things that you can do or not do. Let me kind of summarize this. The C and U means either conditional referencing or unconditional referencing. If you do conditional and call goes 0, if the drive has just been referenced, it won't do it again. It'll say, I'm already referenced, don't waste my time, and it will just exit. On the other hand, sometimes you want to force it to always do a reference operation. So you say unconditionally reference, just do it, in other words. If you pick a constant with a C in it, it will not reference the drive unless it needs to be referenced. If you pick one with a U, it will always do it. Notice when you look at that table there are pairs of conditional or unconditional. Every one of these options pretty much has those two choices. All right, that's what C and U mean. There's W and NW. The wait version means that function goes 0 won't move on to the next line of code until referencing is finished. So it's going to hang your program until you complete referencing. That can be bad sometimes. So there's what's called the no wait version, NW, that will start referencing and just drop through and continue executing code. Now, as you can guess, you're going to have to write some code to decide when it actually finishes referencing. You can't just ignore it from then on. You've got to monitor it and decide when it's done. And we will write code that will do both wait and no wait versions so you can see the difference. All right, so you notice that wait and no wait come in pairs. And then there's one other one here, and there is zero pulse or CAM. If you pick ZP, it's going to use the zero pulse in addition to whatever sensor you've picked, if that's possible. And if you pick CAM, it's not going to use the zero pulse. It's just going to move away from a CAM and stop. Of course, if you're doing a mode that's different, like a limit switch type, then this parameter is obviously kind of silly. It's not going to use it. Okay, we'll talk more about that in just a second, but let's cover the last one, reset. What this actually does is it stops referencing and clears the IPOS referenced bit. So if you're in the middle of referencing and you want to terminate it, you can call reset. Or if you just want to clear the IPOS reference bit to force the drive to always re-reference, you can call reset as well. Those are your types. Let me emphasize this. I've already kind of suggested this. Some of these types are not appropriate with certain referencing modes. For example, CAM is not appropriate if you're using limit switch referencing. And ZP, zero pulse, is not appropriate, for example, if you're using a mode that can't use the zero pulse or if you have an encoder that doesn't have that feature. Therefore, you must be intelligent about which parameters you pick, which referencing modes you're in. You need to stop and think about that whole topic. All right, we have talked a lot. You're probably ready to get on your keyboard and do some programming. We're going to do a hands-on task. We're creating a brand new program, program 8, and we're going to play with referencing. Here's what you need to do in your program. First of all, double check before you even start that you've still got your correct referencing mode. So go to the parameter tree, look at parameter P903, and make sure referencing mode is type 1. I would also suggest that you go to P901 and 902 and set the referencing speeds to 360 RPM and 60 RPM. These are pretty slow, and in a real application you'd probably use something much faster, but you're going to be watching what's probably a flywheel on a demo unit, and it's generally easier to kind of get a feel for what's going on if you're operating at pretty low speeds. All right, next, don't forget to include a wait 5000 at the beginning of your program just to allow everything to stabilize. You're going to use digital output 13 as a ready signal. That's to signal the operator that the wait time is over and you're ready to go. As soon as wait 5000 finishes, turn on DO13 to signal that everything's good to go. Then, wait until all the option inputs are off. Once they're all off, watch DI10, and as soon as it turns on, enter referencing mode. Now you're going to perform an unconditional referencing that waits and uses the cam only. So you'll need to pick the right constants to pick unconditional, cam only, and waiting. Once you've set this up, go ahead and run several referencing runs. Notice how the motor responds when you change either the limit switches or the referencing cam switch. Now in referencing mode 1, only the cam actually is involved in referencing, but remember limit switches are there as protective devices, so I want you to flip the limit switch either the left or right just to see what happens. That would sort of simulate something undesirable happening. Give that a try. Once you've done that, I want you to alter your program to perform unconditional referencing that waits, that's unchanged, but I want you to use the cam plus the zero pulse. That's assuming you've got an encoder with a zero pulse. The standard SEW demo units do, so if you've got one of those, you can count on that. If you have put your own demo unit together, you're going to have to look up your encoder and find out if it has that feature. Once you've made that small change, perform several referencing runs and notice how the motor responds when you change either the limit switch or the cam switch. And then notice the difference between referencing with the cam alone and the cam plus the zero pulse. You should be able to detect a difference. All right, those are the things you're supposed to do in your program. I'd like to make a little suggestion here. I've created a quick reference sheet that's going to be really helpful for all the motion control projects we work on in the remainder of this class. You can see it here. You can download this as a PDF. There is a link in the description of this video below, so go ahead and download that. And let me just quickly point out some of the things it has here. First of all, it has a little handy binary decimal hexadecimal conversion chart there for the first 16 values, which you should be trying to memorize. It shows two very useful system variables bit by bit, status word H473 and control word H484. You will be using both of these a lot, and you do need to know where the individual bits are. It reminds you that motor encoders always have 4096 increments per revolution. That's important. And finally, it shows you the setup of all the lights and switches on a standard SEW Eurodrive demo unit's control box. This is how we've configured the IOs. We did this many sessions ago, but it's certainly helpful to occasionally remind yourself what the switches are set up to do, what the lights represent. Now for this exercise, remember I told you to experiment with the reference cam and the limit switches. Now if you look on this little reminder chart here, DI03 has been assigned to the reference cam, so that's a switch connected to the standard built-in IOs. And then the left and right limit switches are on DI04 and DI05. Also note that DI07 resets VFD faults. You may want to know about that. Be aware as well that DI00 is controller inhibit and DI01 is enable. And then, of course, DI02, DI06, those are just general purpose IPOS inputs. We're not using them for anything specifically here. DI10 through DI17, those are all general purpose IPOS inputs. They can be used for whatever you like in your programs. If you look at the lights, you notice they provide a lot of useful information. For example, DO03, which is one of the built-in outputs, is tied to the reference signal. Now that should turn on when your drive is successfully referenced. So watch that when you're testing your program out. You can also monitor the brake when it's released, if the drive is ready or not. You can detect if there's a fault. DI04 we're not using yet, but that will tell you when you've reached appropriate positioning. Of course, DO10 through DO17 are general purpose IPOS outputs. Different programs will use them in different ways. All right, so get that reference sheet, print a copy of it. It's really handy. One very important note that you should pay attention to, you must turn the controller inhibit, enable, and the clockwise and counterclockwise limit switches to the on position before trying to reference the drive. That means turn on DI00, DI01, DI04, and DI05. If you don't, it's not going to work right. So be sure to do it. All right, enough talk. Pause the video, go ahead and write that program, try to get it working, and then we'll come back and I'll show you mine. All right, hope you got it working and you got to explore referencing. So let's take a look at my program and you can see how I approach this. We're ready for our first program, which is one that explores referencing. You can see I'm in the parameter tree. Remember, we had a few things we had to check first. I'm confirming that parameter 903 is set to reference travel type 1. That means the goal is to wind up on the left end of a reference cam. We'll just pretend, since this is a demo unit, that our cam is roughly in the middle of our travel range. Therefore, we're going to be traveling to the left, which is counterclockwise. Notice also I have confirmed that my two referencing speeds are what they're supposed to be, 360 and 60 RPM. At 360 RPM, that's about 6 revolutions a second, which is modestly fast. And at 60, it's just 1 per second. This will give us a speed that we can easily observe what's happening. All right, that's all we have to do to the parameter tree. Let's go back to our IPOS compiler. I have my complete program in here already. What I'm going to be doing from now on is showing you the complete program and talking about it sort of line at a time rather than keying it in as I've done before. I think you've seen me do that enough, and now we can just focus on the functionality of the code and you can compare it to how you approach the problem. All right, so let me explain kind of how I set this up. First of all, I defined myself two constants. Let's look at the first one here. This one I call opt inputs. Now, if you remember, the system variable INP level B reads all the inputs. What I care about for this program is just the option inputs. I'm not really interested in the standard inputs. So what I'm going to do is create a constant that just isolates those 8 option card inputs. What I do here is I take INP level B, I AND it with a mask that isolates just the bits of interest. Then it shifts it by 8 to the right, which shoves off all the standard inputs and just preserves the option inputs. Therefore, the bottom 8 bits of this constant will be the inputs I'm interested in. Secondly, remember we were supposed to use digital output 13 as a kind of ready signal. Therefore, I've just defined ready as a 3. Now you may wonder, what is that 3? Well, that's bit 3 in opt-outp IPOS. That's where DO13 is. I'm going to be controlling that bit. Therefore, this is just its bit number. Again, just makes my code more readable. All right, next, we come into the main code itself, and we do finally have some actual initialization. We have 3 lines of initialization right here. We do this just once when the program is started up. You can see the first thing I do is I turn off all the lights attached to the option outputs. So opt-outp IPOS is set to 0. Then I call the wait function with a time of 5,000 milliseconds. That gives my system time to stabilize. And when that is over, I call the bitset function to turn the ready signal on. So what I do is I pass it opt-outp IPOS as the system variable. That's where I'm going to change a bit. And I send it that ready constant, and that will turn bit 3 on. As soon as the light turns on, I'm ready to reference. Okay, that's all the initialization. We now go into our endless while loop. And the very first thing we do is we just need to wait until all the option inputs are off. So I say while opt inputs not equals 0, just sit and spin your wheels. This is one of those while loops that doesn't have a line of code. It just ends in a semicolon. As long as any one of those 8 switches is turned on, it's just going to sit here and spin until I turn them all off. This will check that all the option inputs are off. Soon as that happens, I go into a second while loop that does exactly the opposite. I wait for at least one switch to be turned on. So I say while opt inputs equals 0, sit and spin your wheels. Ideally, of course, the user flips DI10 on, which is what triggers referencing, but actually if any switch is flipped, it will get out of the while loop. So what I have to do then is check to make sure it's the right switch. What I do is I use that constant DI10, which is defined in IOB.h, and I say if DI10, in other words, if it's on, then go ahead and start referencing. If it isn't DI10, of course, then it's going to fall through there, go back in the while loop, and start watching again. This will weed out any inappropriate inputs. Pretty simple. Finally, we get to the meat of the program, which is to call the referencing function. And what we were supposed to do is do unconditional referencing that waits and uses the cam but not the zero pulse. What I do, therefore, is I call go0 with the constant go0 uw cam, which fulfills all those requirements. And that is absolutely it. Pretty simple piece of code. Let's just compile this thing, make sure it's clean. And it is. We'll run it and go to our control box and exercise our program and see if everything works. This is our first program that produces actual motion. Therefore, we have to get our switches set up correctly for things to work right. As I mentioned, we have to remove controller inhibit from the VFD and enable it. We have assigned 2 bits to that. Of course, controller inhibit is permanently assigned to DI00, but we've assigned enable to DI01. Both of those inputs must be on for the VFD to be able to produce motion. Now, we didn't have to worry about this with our blinking lights program. The VFD does not insist on the controller inhibit being turned off and the enable being turned on just to blink the lights. But if you're going to move the motor, you do have to play by the rules. Therefore, I'm going to turn DI00 on. I'm going to turn DI01 on to enable the drive. And the minute I did that, guess what? My limit switch is tripped. Okay, we have to remember limit switches need to be both on because limit switches are active low. That's kind of a failsafe. Therefore, I'm going to turn my limit switches on. They're connected to DI04 and 5. I'll flip both those on. Now my VFD is flashing a fault code. I have to clear that, and I'm going to do that by toggling DI07, which is the fault reset switch. I've just cleared my fault. My VFD is resetting itself. And now it's running, and everything is good. It's happy. I can see from my control box that digital output 13 is lit. That means I have gotten past my wait time. I am now ready to trigger referencing. I'm going to turn DI10 on, which will start referencing, and hopefully what I will see is my motor rotating counterclockwise. Let's see if that happens. And it certainly is, and it's spinning along at what very clearly looks like 360 RPM, not 60. That's good. Now let's see if referencing works. What I'm going to do is trigger my cam, which is connected to DI3. What should happen is the drive should slow down. It should keep turning clockwise because it's going to move over and off the cam, but it's going to do it at the slower speed. And then as soon as I turn my cam off by flipping off DI3, it should stop. Let's confirm that happens. All right, it very clearly did slow down. Now I'm going to stop it. And referencing is over. Pretty nice. Looks like everything worked, but remember we were supposed to explore what happens with our limit switches. So I'm going to trigger referencing again by turning DI10 back on. I did turn it off earlier. You can see now I'm referencing again. I'm going to turn my right limit switch off, DI04, and that tripped a fault. I will flip that switch back on and reset my VFD by toggling DI07 to clear that. You can see, therefore, if I trigger my right limit switch when I'm supposed to be moving left, the VFD definitely doesn't like that. It thinks something really weird is going on because that's not even a limit switch you should be able to trip, all things being normal. Let's start referencing again and trigger our other limit switch, the one on the left side. This was interesting. It didn't fault. All it did is reverse direction. If you think about it, that makes sense. It bumps the limit switch and it says for some reason you didn't trip the cam. Maybe you were already past the cam before referencing started, so I'm going to move clockwise to try to hit that cam. All right, let's assume that's what it's doing. First thing I'm going to do is say I've moved off the limit switch. I'm going to turn DI05 back on so it knows I'm off the limit switch. And now I'm going to trip my cam and see what it does. You can see it just reversed direction. It's backing off the cam. I'll shut off the switch. We're now off the cam and it's happy and believes it's referenced. Therefore, we can see there's actually a little more to referencing mode 1 than we first thought. It actually does treat the limit switch in the direction it's trying to move a little differently from the other limit switch. All very interesting. Anyway, worked pretty well. I'm going to now stop my program. And I'm going to make one little change. We were supposed to set it up to use the 0 pulse. I do have an encoder that supports a 0 pulse, so all I'm going to do is change cam to ZP, recompile my program, and run it. And I'm going to see if there's any difference. I'm going to do another referencing operation. I'll trip DI10. And then I'm going to hit the cam, DI03. We slow down. We're coming off the cam. I'll turn off DI03. You notice it didn't stop immediately. And the reason is it was looking for the 0 pulse, and it took, in this case, part of a full revolution to get there. Definitely a difference here. I'm not going to demonstrate doing all the other things with the limit switch. It behaves pretty much the same way. So you can see the difference between 0 pulse and not 0 pulse, and we've explored this referencing mode pretty thoroughly. That's it. All right, well, it's time to move on. Hopefully that all worked well for you. We're now going to explore the difference between wait versus no wait functions. Several functions in the IPOS library have the ability to either wait to complete before they move on, or the no wait version where they just run into the next line of code. I want to explain the difference between these and why you'd use one versus the other. How does a wait function behave? What are its qualities? The function starts the task and then it just idles until it completes. In other words, it doesn't move on to the next line of code. So the task is happening, but your code is basically hung until the function is finished, and then of course it moves on. Now sometimes this is desirable because it gives you very simple, easy to understand code. However, the disadvantage is the function can get hung up if whatever it's doing never finishes. For example, if you go into referencing mode and you never successfully complete referencing, the program's just going to be stuck waiting for referencing to complete forever. That's not so good. In certain circumstances, this really can mess you up. It's not a great thing always. And that's why the no wait function does exist. No wait functions behave like this. The function starts the task and then just immediately moves on. It gets it rolling and then goes to the next line of code, and your program can continue doing its thing. Of course, the downside is it's up to you to figure out when the task completes. If you're referencing, for example, that's going to take time, maybe even several minutes, depending how you're doing it. Your code needs to know when it's done so it can react appropriately. And that means, as you probably have guessed, that you have to monitor various bits and status word or other system variables to know when it's finished. But the advantage is you can do other things while that task is running. Maybe something just really simple like blinking a light to show that something's happening, but maybe something very complicated that you're doing while you're waiting. It's really up to you. The advantage here is it's a lot harder for your program to get hung up because you're always in control. Your code is always running, and if you write it correctly, then it can recover if that function never completes. We'll be exploring how to do this as we go along and develop other programs. The referencing function does have the ability to do a no wait. You know that already, but we're going to explore how you manage it. Let me give you some guidelines for doing referencing using the no wait version. You issue a goZero function call, and you make sure the constant that you pass it contains an NW, which means no wait. There are a number of these, so you can pick from the available choices. You pick one with NW, and it won't wait. If you put one with a W, it will wait. The way you know it's completed referencing is you watch the IPOS reference bit in status word, that's H473. What it will do, shortly after you call the goZero function, it will change to 0. Now maybe it was already 0, but if the drive happened to have been referenced, it'll be 1 initially, there'll be a brief delay, it'll change to 0. That means the referencing operation is started. So you want to watch it first, to watch it go to 0. It may actually be 1 very briefly, and you don't want to be fooled into thinking that referencing is already finished. So watch it go to 0, and then watch it again until it changes to 1. When it changes to 1 after it's changed to 0, it means referencing has successfully finished. Now, during referencing, which can take some time, you can do other things. So your code can do other things, but you do want to keep checking that bit. As you check that bit, you'll know when you're finished. There should always be a way out. If referencing never completes, there should be some way to get out, terminate the referencing operation. And there are many ways to do this. You can monitor IOs and have an IO bit that escapes. You could use a timer. You could do any number of things. It's really up to your creativity. Now, when you're using referencing modes 5 or 8, those are the no motion referencing modes where they just reference immediately. You don't actually have to watch IPOS reference to make sure it changes to 0 because these change it to 1 almost instantly. You might actually never see it change to 0. So if you're using just 5 or 8, just make sure it's gone to 1 and then move on. But any referencing mode where it moves the drive, you're going to have to verify it goes to 0 and then verify it goes to 1. That's a difference. And that brings us now to our next hands-on task. We're going to just modify the existing file, program 8. You can probably guess what we're going to do. We're going to convert our program to no wait operation. So here's what you're supposed to do. Modify the program. It should still do unconditional referencing, but it shouldn't wait. This should be a no wait version. And I do want you to use the CAM plus the 0 pulse if the 0 pulse is available on your particular unit. And here's what you're going to do while you're waiting for referencing to complete. Remember I said you can do something. I'd like you to flash the light attached to DO10. Flash it at 100 millisecond intervals. So every 1/10 of a second, that light should toggle from on to off to on. And that blinking light will indicate referencing is running. When referencing finishes, turn the light off. You don't have to build any kind of escape condition in yet. We're going to do that later. So just convert it to no wait referencing and add the blinking light. Go ahead, pause the video, and do it. All right, hope that went well and you succeeded. Let me show you my code and you can compare it to yours. All right, let's start work on version number 2 of program 8. You can see I've got my modified program up. What I'd like to do is just go through some of the changes I've made. A lot of the code is exactly the same, but of course a few things did have to change. One of the things we definitely need to identify is the reference bit in status word. When we use the wait version of goZero, we don't have to worry about figuring out when referencing is over because the function simply hangs the program until it completes and then the function moves on. We're going to be using the no wait version, which means we have to decide when referencing is finished. That means we need to monitor the IPOS referenced bit in status word. Status word, as you know, gives us a pretty thorough picture of what the VFD is doing. What I've done here is I've created a constant called referenced, and I've isolated that bit, which happens to be bit number 20. So I took status word, I ANDed it with this hexadecimal number that happens to have a 1 in the right location, I shifted the bits right 20 positions, which puts the IPOS reference bit at the very bottom. And so all we have to do is see if that bit is 1 or 0 to know if we're referenced or not. Pretty simple. We're also going to be blinking a light. We're going to be blinking DO10. And to do this, I'm going to be using that bit move negative function to toggle the bit on and off. As you remember from an earlier program, we have to read the existing status of the bit in OutP level B, but we have to change it in opt-outP IPOS. I've defined two constants here, identifying the location of the right bit for DO10 in each of those. They're not in the same place. It's bit 0 in opt-outP IPOS, and it is bit 6 in OutP level B. I have two constants for that. Of course, our ready constant remains the same. That's the change to our constants. Let's move on. Nothing different in the beginning of the code. The initialization's the same. Also right here, the while loops that monitor the input bits and also the if statement that checks DI10. No difference there. That's exactly the same code. Right here, of course, we do have our go0 function call, and notice we're using NW instead of W, so this is the no-wait version. Notice also we're using the 0 pulse. All right, that's familiar stuff. Now the new code. Remember what I said, once you launch referencing using the no-wait version of go0, the very first thing you have to do is wait for the reference bit, the IPOS reference bit in status word, to change to 0. It may be 1 very briefly, and then it will change to 0 to confirm that referencing is started. What I'm going to do, therefore, is use a while loop, and I'm just going to say while referenced. In other words, while that bit is 1, sit there and spin your wheels. As soon as that bit turns to 0, which will happen pretty quickly, it will exit the while loop and move on to the next one where it starts watching for referencing to complete. That's what our second while loop is for here. It says while not referenced. In other words, while the reference bit is 0, sit and do something else because referencing is going on. So we're not just sitting spinning our wheels. Remember, we're supposed to be blinking a light. That's why I have a set of curly braces with 2 lines of code in there. This is my light blinking code. As soon as the reference bit turns to 1, however, the while loop will exit and we're done. Let's look at my light blinking code here. This should look familiar. We're using bit move negative, and we're copying the appropriate bit out of OutP level B into opt-outP IPOS, but we're inverting it every time we do that. That'll make the light blink on and off. We're using a wait 100 to give it a 1/10 of a second blink time. Of course, we could do something more exciting in here if we wanted to, but we're doing this just to show that you do have the opportunity to run code while referencing is happening. And of course, this is good because by blinking that light, it confirms something's happening. Now, as soon as the while loop exits, in other words, referencing completes, the very last thing we have to do is just turn that referencing light off by executing the function bitClear on opt-outP IPOS and clearing reference 1, the appropriate bit. And that is it. That's our code. Not a lot of changes, not too complicated. Let's compile this, make sure it compiles fine. And I'm going to run it. I'm going to turn controller inhibit on and enable on, make sure both my limit switches are on, and then I'm going to trigger my referencing operation. And 2 things should happen, of course. The drive should start referencing and the light should start blinking. Let's check that. Well, you can see the drive is running clockwise, so it's seeking the cam, and the light is very definitely blinking. Now I'm going to trigger the cam by turning DI03 on. You can see referencing completed as expected. So that's it. That is no wait referencing. Okay, well, moving on. We have learned how to use the go0 function. I'm going to introduce you to another function related to it. This is called the axis stop function. As you can guess from the name, its purpose is to halt the axis. There are definitely times you just want to come to a stop. You can see it has one parameter called type. There are several different stops available. As you can guess, constant b.h defines a few constants, in fact, 4 of them. So here they are. AS rstop, H control, P stop, and enable. What's the difference? ASR stop stops the access using the rapid stop ramp. That's parameter 136 in the parameter tree, and if there's a break there and it's enabled, it will also use the break. So it picks a particular ramp, typically a ramp that does a very quick stop. Of course, it all depends how you've configured that ramp in the parameter tree. H control stops using the regular stop ramp. There are two of these in 131 and 133. Again, how fast it stops depends what value you put in there, but this is just what you might call a normal stop, not a quick one. Probably do this in just ordinary operations, whereas rapid stop might be more for an emergency or something where you want to stop really quickly. There are also two positioning ramps in parameter 911 and 912, and you use the P-stop version if you wish to use those. You can see the only difference here is which ramp the VFD is going to use to stop the access. And what happens depends what numbers are in those parameters. So this is a little bit flexible. It just depends how you've set it up. And then the final type is AS enable. After you stop the access using RStop or H control, the access will not run again until you re-enable it. So you have to do an access stop with AS enable sent in. That re-enables the access after a stop. Don't forget that, because if you do forget to do that and you don't re-enable it, you will get no further motion. The drive will just be permanently disabled. This is a very common mistake. Just remember you've got to re-enable your access after you've done a stop if you've done it with RStop or H control. So, time for a third hands-on task. Again, we're going to just be using program 8. So we're just modifying it. This is sort of version 3. Here's what I want you to do. I want you to modify the program so you can halt a referencing operation either using the controller inhibit switch or the enable switch. These are DI00 and DI01. These switches are normally both turned on when you're doing operations. What you're going to need to do, therefore, is turn them both on the control box before you run your program. And you'll just do your normal referencing that your current code does. You remember you've done a no-wait referencing. But if you turn either DI00 off or DI01 off or both off, it will halt the referencing right in the middle of the operation if necessary. Of course, if you don't halt it, then referencing should operate normally and could complete normally. I want you, if you do a halt though, using controller inhibit or enable, to halt it using the rapid stop ramp in P136. That means you call access stop with the RStop constant. Of course, DO10 should flash during referencing, and either when you finish referencing or when you halt it, it should go out to reflect that. All right, go ahead, pause the video, and give it a try. Well, hope that went well. Let's see how you did. Here's my code and how I handled it. All right, well, this is version number 3 of our referencing program. It's pretty much the same as the previous one. It's using the no-wait version of Go0, but we're adding one extra feature. We're giving the ability to escape out of it. Remember the other one, the only way you could really finish it is to complete referencing. With this one, we're going to give 2 escape clauses besides completing referencing. Either you turn controller inhibit off or you turn enable off. If either one of those goes to the off condition, the referencing operation will stop. It will clear the reference bit and go back and wait for another chance to do it. And of course, the referencing can complete normally as well. This is actually very simple to add this functionality. We just have to add a few lines of code and that's it. Let me show you what they are. First thing we need to do is we need to put this line in here right at the beginning of the while loop. This is a call to access stop where we re-enable the access. We should make it a habit of doing this because if there was an existing access stop, it could keep the drive from functioning. What we do is we do that call just to be sure the access is ready to run. Then we have our usual while loops and the if statement to look for the condition to start referencing. We have the call to go 0, no change there. We have our while loop that looks for the reference bit to go to 0. And then we have a line that's changed. And that is our second while loop that is waiting for the referencing operation to complete while not referenced. Notice we've added 2 extra conditions to check. We are ANDing it logically with DI00 and DI01. What we're saying is, while it's not referenced, and DI00 is on and DI01 is on, sit in the loop and blink the light. But if reference completes, or controller inhibit goes away, or enabled goes away, or any combination, jump out of that while loop. As soon as it exits the while loop, it turns the referencing light off so it stops blinking, but then it has to decide, did referencing end normally, or did we terminate it early, either with controller inhibit or with the enable signal? After we turn out the light, here's what we do. We put an if statement here and we say if not DI00 or not DI01, in other words, either one of those terminated the referencing early. If either of those happens to be true, we do an access stop using the rstop. That's the rapid stop ramp. And then we call go 0 and we do a reset. That just removes that IPOS referenced bit. So we do those 2 things, and that terminates everything early. Of course, if referencing terminated normally and successfully, we don't go in here. We just go back to the beginning and wait for another trigger for referencing. Pretty simple and straightforward, just a few extra lines of code. Let's compile it and run it. See if it works. We'll go to our control box. We will turn on controller inhibit and enable. We'll start referencing up, and then we'll try various possibilities. We really need to test 3 of them. We need to check for a normal referencing. We need to check for an early stop with controller inhibit and an early stop with enable. Let's give all these a try. First thing I'll do is start referencing by turning DI10 on. And we are referencing. Now let's do just a normal reference operation. I'll trigger the cam. We're moving more slowly, and we come off the cam, and we stop after we go past the 0 pulse. That's a normal referencing operation. Worked just fine. Let's trigger another one, and we'll try stopping it early with controller inhibit. I'll turn DI10 on. We're referencing again. I'm going to turn controller inhibit DI00 off. Click, we stopped immediately. All right, I'm going to turn controller inhibit back on. And I'm going to start referencing up one more time, and this time I'll end it early with the enable signal. I've started referencing. Now I'm turning enable off, and click, it stopped once again. It appears that our program does everything expected of it, and that is always encouraging. And there we go. That is the end of session 9. That's our first motion control session. We did 3 programs. You learned an awful lot about referencing, so hope it all made sense. In our next session, we're going to look at positioning. See you then.